Okay, this is the key idea about how we break or how the Virginia cipher. Let's say we have a ciphertext which has n letters, and if we arrange these n letters into r columns, then each column should have n over r letters, or slightly plus minus 1 or something like that. But if n is big enough, then this is the same as that one, right? So let's just assuming we have each column in this table has n over r letters on it. Then if we choose two letters from the same column, and if we got this, we have that many different ways to pick, right? And if we choose two letters from different columns, then we are going to have that many different cases. So that's the number of cases we could pick two letters randomly from the same column or from the different columns. And we already checked that each column is kind of monoalphabetic. So what is going to be the expected number of pairs for the randomly chosen one from the same column is going to be like this, because it's monoalphabetic. But from the other cases, we have that coincidence, right? So that expected number of pairs should be sum of this one and that, right? Okay, so some arrangements, we are going to get this one. So the probability of both letters are the same is going to be that cases out of just random choice of two letters from n characters, right? So out of this many possibilities, this is going to be get the chance, right, to pick the same number from the first column, from the different column, but still we got the same letters from different columns, right? That's the kind of probability, the cases for that. So this is going to be the probability of picking the same letters from the ciphertext, no matter whether it is on the same column or different column. Okay, from calculation, we know this should be the cases for getting 2 out of n without order is n times n minus 1 over 2. So it's going to be arranged like this, but en is this one. So when you look at this one, actually 2r is common denominator. So putting that to r, 2 cancel out, and r should be arranged here, and n could cancel with 1 of n from each of these terms. So somehow we are going to get this one. Please check for yourself. So that is going to be the probability to pick same characters, same letters, okay, from the ciphertext, which has n letters on it. Then this is precisely the interpretation of IC, the index of coincidence, right? So IC should be in this one for that cipher case, right? So we should have this one. So if we solve this one for R, then from here, then R is going to be same as this, and we use IC here. And whatever we got, that should be the length of the keyword for this Virginia cipher. Okay, so that's the whole idea here. Okay, so if you have the message of length n and IC is encoded using a Virginia cipher, that is with that condition, right, then the length of the keyword is given by the formula this, right? Of course, this keyword may not be the real word, practical word, right? Because if that word has same characters on it, we only use once, right? So it could be just any string of letters. But anyway, R from this formula will giving us the length of that keyword. That's the key point. So altogether, from the Kosinski test, we could get kind of guessing of the length of keyword. It could be multiple of certain prime numbers, right? And from this Friedman test, we could get certain length of keyword which is used for that cipher. So if we combine these, we could kind of get very accurate the length of keyword altogether. So from Kaczynski test, it's just maybe several possible lengths, right? But if it comes with Friedman, then definitely we could get the really accurate length of keyword. So for example, from the Kaczynski test, if we suggest the length of keyword is multiple of 7, but from Friedman test, R is very close to 15.3, then 14 is going to be the reasonable results for that.